So let me first introduce the speaker, Parfait, if you would come back on camera. Parfait Ashad is co-owner and chief quantum information officer at Lighthouse DIG and a research affiliate at the MIT Media Lab. Holding a PhD in quantum computing, he specializes in quantum algorithms, hybrid optimization, and AI-driven modeling. He builds innovative solutions that help organizations and cities solve complex challenges, bridging the gap between advanced research and practical impact. His mission is to scale quantum and AI technologies from the lab into real-world applications that transform industries and society. So welcome, Parfait. You can get started.
Thank you. Thank you for this introduction. And also thank you for having me here and also for supporting this project, Network Adjustment Project, and seeing how quantum computing can be applied to this project, optimizing aircraft utilization. Here goes the roadmap of this webinar that I will start with a short introduction with the problem definition. After that, I will jump into the model development and his extension, and dive deeply in the modelization and quantum computing, followed by a result and discussion. And at the end, I will focus on the main conclusion. Before understanding this, we have to understand that the aircraft network planning is a step-by-step process. The process starts from long-term planning by choosing which route and which benefits that we want, but the company want here. And we are talking about like 1 year ago planning. And moving to the midterm, that we are talking about 3 months and so on, as focusing in the scheduling and fleet decision. After that, we move to the crew and the short-term adjustment planning. All this stage or all this step adds complexity to the planning and to the model. And we will see how optimization and quantum computing will help us to be more efficient and more consistent. Now, focusing in the case of Vueling, the scheduling process nowadays is manual. That means that optimal solution is not always guaranteed. The process is slow. There could be a lot of scheduling error, and many requirements are unmet. That means in practice, only few adjustment optimization are performed. So, seeing this, we can see that our goal and benefits are very clear. As goal, what we have to do is like given the original network, we can find some way to modify this to maximize the aircraft utilization, because we are talking also about low cost, that maximizing the aircraft utilization is very important. Okay. At this point, we didn't take into account, we didn't analyze the expected revenue and operational costs are not considered in this model. Okay, but is related, totally related. While we are maximizing this aircraft utilization, we also minimize the flight rescheduling. This is very important, and we will see it in the tactical part. By minimizing this flight, at the end, what we want to do, what we want to achieve, is to ease the network operability, to facilitate this network operability for the given department. That is directly the expected benefits that we can see from the scheduling department, that we will move from manual to automatic modulation, they will gain a lot of flexibility and time efficiency. And also for the operational department, we are seeing that we can discover, we can have like some pattern, flight pattern that can help us to make decision and to be also more efficient. And obviously for Vueling, this could help a lot for increase their profit. Before dealing in the model, we need to understand a little bit more what network adjustment means, problem means. Is a problem about optimizing like a bunch of flight and aligning a schedule and resources according to some restriction that could be operational and also could be like a regulatory restriction. So to have some kind of view, like a horizontal view here, what we are saying at the end of the day is that we have one side, the schedule planning, that is NP hard problem by himself. We have the fleet assignment problems and subject to operational and commercial and regulatory problems that are could be very hard to model also. But at the end, we will have the optimal network. But this also, one thing that we want to make sure that our audience also understand it well is that according to this NP hard problem, the problem that we are trying to solve, we also need to model the problem somehow that we can minimize the number of the variable. And we know that in quantum, the variable can be related directly on number of the qubit. And in this quantum era, where we have few qubits, so we need some kind of a strategy that help us to design some kind of mathematical objective function, but also allow us to reduce the number of variables. So, as we have seen, so we need like a first step of all this work, we need some kind of strategy. So our main strategy is to reduce the complexity that we have seen that in each stage, long-term strategy, mid-term strategy, and the short-term strategy add in the process some complexity. So we need a strategy that can help us to reduce this complexity. How we do it? Instead of modeling with individual flights that we can see here, we model with a chain of the consecutive flight per aircraft that we call like a super rotation. By doing this, what we are trying to do is we are reducing the number of variables that we will need to make all this synchronization and also work with the turnover flight and a lot of things here. Those variables that we are talking about are somehow our decision object for the model that we are talking we are focusing on. So the sub rotation are the sequence of 2 to 4 flights that can match in each airport that we need some kind of variable like an airport that have the beginning and the ending in this airport that we create like the base. So here we can see it that here we can have the base that is the input airport that here is Amsterdam in this case and end also with the same base. That is what we call base. And between them we have this airport that can make like some kind of a schedule that we call them like rotation. Okay, here is another example, and here also downstairs is another example. And our main input problem is the original network. Original network is the network that the team have built like a year ago from the long-term strategy. That is the road that is decided manually and also the benefits that they want. So this is our original network where we have those regular flights with their initial departure and the arrival time. They have the associate base airport and also they have associated plane that we call the set like soufflet. That is kind of plane that we have. What we are talking about is look like this is some kind of input information of our model, where we can see that the color represent the different flight, different subflight in the Vueling systems, and the rotation is the whole sequence of the aircraft platform perform each day. And the subrotation, in this case, we can see here that is like a group of 2 or 3 or 4 flight. In this case, we can see that we can have like mainly a round trip. So having this, one of the strategy that also we need to achieve the problem and reduce the number of qubits is to see how we generate this candidate, this subrotation candidate. But before doing this, we need to understand that we have either input this original uh, network, and we create some kind of optional flight that our objective that we pursued is to fulfill the flight network. And this also help us to make some kind of modification and cancellation on this flight that can be scheduled or not. So we use this optional flight that we fulfill in our systems, and we try to modify them or not and see how we can optimize the whole stuff. And the way that we use to generate this candidate of subroutine are given in the left. We can see that given the subrotation, we have like 3 biggest operation that we apply. The first operation is the retiming. That means the ability of changing all the block schedule. That means we can change, in this case, 8:30, we can change 30 minutes earlier, and this change the whole subrotation schedule. We have another operation that we can do over the rotation, that is the subfleet change. So we can change the plane that perform this flight, or we can change also the base. That is like we can flip the base airport that in the original scene we had Barcelona like the base, and here we are seeing that we have Orly. So this operation that we can change, and also this, let us say that the minimum turnaround time also required between the flight also are also maintained. That is important. So according to this concept that we have, we need to dive a little bit in the math by defining some kind of objective of the optimization problem that we are trying to solve. So we need to select this subrotation to operate. For that, we define 2 sets, that original mandatory subrotation, and the another hand also we need to decide to have this optional rotation set also. By having this set, what we need is to find a candidate as the copy of the original one. So with modified time, according to the operation, the 3 operations that we have seen before, that is modified time. This is the retiming, modified subfleet, or modifying the base. By using also the binary decision variable, that is the way to select or not the subrotation. We will talk a little bit about this further, that all this strategy help us to see how can we, at the end, design the objective function according to the restriction. Okay. And the another thing that we need is we need to calculate to know how many aircraft do we have in the base airport. Because knowing that, we can design the model that makes sure that we cannot have more outgoing flight than the flight that we have on the airport, base airport. And also, this will help us for the balance equation. At the end, taking into account all these strategies that we have talked about, and also uh, um, all these input information, we are able to design the objective function, the daily objective function, which objective is maximize the flying time according to the balance constraints for the incoming and outgoing aircraft. And we need to make sure that the mandatory flight must be scheduled once in the subrotation, but the optional flight could be scheduled once or not. By seeing this, we need also to understand a little bit this problem that we have. Let us extend it in the daily problem and see the operation limitation, because in the airport, we have like an airport curfew. That is the time where flight cannot depart or arrive. So in our model, we need somehow to inform this information. Even if this limitation we didn't apply directly in the model because we didn't have enough qubit and we want to reduce the number of variable, this limitation, this operational limitation, we use them to embed in the subrotation generation. So the early depart and the late arrival also, the restricted number of the departure here, we also need to make sure the slot, that is the interval that the exact number of flights must arrive, because this is some kind of contract that the company has with each airport. So we need to respect this information and also the non-overlapping flight. That is the minimum distance between the flight with the same origin and destination. So we need to inform the model somehow with all this. But if we take all these operational limitations and we put them directly in the model, we will deal with a bunch of variables. So in instance, a lot of qubits that we don't have yet. So we need some kind of a strategy here, like divided and conquer by dealing with this operational limitation. At the end of the day, what we are talking about is this one. The optimization process is launched once the sub-rotation generation are done. So we have the reference, that is the original network generated very early, and the optional set of flight that we define mathematically. With this, we add also the constraint about the slot, the overlap time, and all this, and the number of aircraft. By having this, we can use the optimization. We can design some kind of mixed integer programming by solving this classically, if we want to solve it classically, or solve this quantumly. Okay, but all these strategies help us to reduce the number of variables, because also the most important, the most powerful solver, classical solvers, also have the limitation of number of variables. So we need those a strategy to do it. At the end, we have this optimal scheduling. How we use to solve this optimization process is to divide, like as we said, divide and conquer, to divide and two stages. In the first stage, what we did is to see how can we maximize the flight time. Let us remember that we are talking about the low cost company, that having the aircraft in air is very important. It's very important. So we need to maximize the flying time. And the second step is some kind of a tactical decision because of 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 having this maximized. If we maximize the number of flight that we have, maybe we can have some kind of solution or some kind of combination of solution that could be very difficult to be used to be realized in the operation department. So to make it real, we need to introduce some kind of things that we call retiming. That what is do is to make sure that the end solution are not too far away from the original solution, that we can change few things to meet the optimal schedule that we are looking for. Okay, this was the thing that we have seen was about the daily model, but also we need to think a little bit about the weekly planning, because we need somehow to maintain all the pattern that's working daily in the weekly pattern. So we need somehow synchronize certain flight departure along the week. So, by instance, along the month also. So we need some kind of synchronization variable where a new variable emerge to compute this time where each flight are synchronized. So we add this synchronized flight, and we oblige ourselves that this flight must depart at the same time. And this problem, if we want to solve if we want to solve all these problem, and we want to make all these problem to be all the variable or this flight to be synchronized, maybe we can have like a time constraint solving problem. Why? Because this problem that we are solving is like a subset of one biggest problem that we need to solve in the in Vueling, in the aircraft optimization. That solving this smallest problems, we need that at the end result have to be very, very short in time. So here we want to solve all the whole problem in 5 and 10 seconds. So this is very, very important to make sure that we can that all the things that we are designing are feasible or not. So at the end, the strategy or the operational stuff that we use to solve all these aircraft problem is given by this diagram. So step 0, we make the daily optimization. Step 0 prime, to say somehow, we make the feasibility. We see that after having the optimization, daily optimization achieved, we see that if the synchronization is feasible or not. If it's feasible, we move to the thing that we already seen, that is the maximum the flight time that we call the block time, and also minimize the retiming time. But the thing that also we are doing here is each stage fits or the optimal solution of each state are injected as like initial point for the next step. By that way, what we are doing is we are making sure that the problem that we are solving is going to converge or not. So after seeing the way and the strategy that we use to design the objective function according to some restriction. Now we need to think about how can we map this into quantum computing or in the quantum computers. According to the size of these problems, we have the the opportunity, the feasibility that we have is to map this problem to quantum annealing. So the framework to mark this problem and quantum annealing is called QUBO, quadratic unconstrained binary problem, or there's also constraint quadratic modeling. So the thing that we know how we know it is having this MIP programming problem. We can map this MIP problem into the QUBO. So the restriction, the only thing that we need is to convert the restriction to the penalty function. So it's the thing that we are seeing here in this slide. So the mandatory flight that we have this restriction, we can convert them into this following penalty function. And the optional restriction also we convert to this penalty function. And the advanced constraint, like the balance equation, also we convert by this way, and the overlapping that we convert by this way in this penalty function. This is when we are dealing with QUBO, because we know that QUBO is directly solved by DWave, is directly solved by the DWave solver. But if we are thinking about CQM, that is like a constraint quantum quadratic modeling, we can use directly the MIP modeling that we have without dealing with this penalty function. So we can map this problem directly to the quantum computing, to the DWave, by using the CQM solver. Once we do that, it's time to see the results. Okay, here we can see that by dealing this problem and solving like close to 4K flights, we achieve like adding close to 6% new flight to the original network. And also we optimize close to 4% the flight time. And in the retiming, this shows us that we have a bunch of candidate optimal solution that the Department of Planning can use. So we have like 90% let us say that of possibility of this optimal solution, that they can choose that perfect. Maybe we take this or that or not. That is very interesting to see that we have a bunch of possibility on that. And the optimized network schedule could be look like this, where we can have this part is the new optimal flight that we are generating, and we are proposing to the planification team. And we can see also the synchronized flight here, and we can see also the retiming flight according to the original flight. As a result, we can also say that the mathematical formulation is fulfilled for solving this most operational condition, and because of the strategy that we think about, that is like a divided and conquer, because of if we're trying to solve like in only one objective function, subject to all these restrictions, will be very, very, very difficult to solve it. So the strategy that we design and the mathematical that we develop help us to see how can we solve this problem classically, also quantically. And they provide tools that we are achieving here to automate this process with Vueling specification is achieved. Okay, let us say that the project is still under development, but the extending of the scope of this project to correct the original work is is faced. And also we are improving in the optimal flight time also to include more optimal flight and several origin and destination. And also we are doing some kind of research and seeing that about the synchronization approach, which we can improve and how can we improve them also to make it more feasible and easy to be used. Okay. Technically, we can say that the model validation has been done, that we validate like with 6 network adjustment scenario, range to 100 to 2K variable, perform in DWave, DWave systems, um, Kubo solver, and also CQM solver. And we made some kind of benchmark, and also we benchmark with the classical solver, here C++ and simulating annealers and also Groovy to see how these perform. And we have seen that in very short time, between 5 and 10 seconds, the CQM solver maintain quality and speed even for large instance of problem. That is very, very good. And in the strategical view, we can say that the potential and the scalability of this hybrid quantum computing for solving this real optimization problem are met, and also in this aviation sector. Here we can see some kind of table where we show the scenario and the number of variable and the times, the running time that we have. At the left hand, we can see the hybrid solver BQM, that the binary quantum quadratic modeling, and the right hand we can see the CQM, where we can see that the CQM achieve all the optimization solution in all the scenario, and in this time that was also required for Vueling and seeing. One thing that we have to add, Vueling doesn't need to achieve the most optimal solution. All the candidate solution are very interesting for them. Okay, and this is important because sometimes if you try to achieve the maximal optimal, if you achieve that, maybe applying this in the real to reschedule all the flight could be very, very difficult. So is not mandatory to achieve the optimal solution. And this also is very good news for us by dealing with these techniques that we are talking about. For the discussion, yes, is like that. Yeah, perfect. They deal with a hybrid solver to reach the optimal in all the evaluated scenario, both block time and retiming. That is important. And also it's very important to see that this platform and this solution is capable of handle like a lot of binary variables that we are talking about, 100 million quadratic iteration and explicit 100K explicit constraint. That is a lot. And if we take account this strategy that I was talking here about, we can use this to solve the problem easily, and is important. What we have seen, and makes a lot of sense, is that the CQM offer greatest expressiveness than Kubo. Why? We can explain a little bit this and make sense. Because DWave developed from this CQM is that we can embed directly the let us say that the MIP, the mix programming, integer programming into the solver. We don't need to remap the restriction with the penalty function. That means if we can do it directly, we can achieve greater expressiveness, and also we can go very straightforward. That is a very good news also. So that means if we are able to design the objective function according to the restriction, and we have it clear, and we make sure that this will work according to some strategy, we can map this directly to the DWave solver. And this is a good. And also, we already said that, yes, a highly competitive about time and number the variable, and the result is showing that these problems are very robust and scalable in performance. Like conclusion, what we are saying that we have shown and that the network planning optimization problem that is very NP hard problem because it's the combination of several NP hard problem and can be tackled with this hybrid quantum computation. That means that we are thinking about real problems. Okay, and Vueling here is working with this problem to not only the toy example, but to move forward and to put this problem in production. That this is very very good good things to know. But it's important also to say that we are in this quantum era where we have few qubits. So to do all this stuff, we need a very good strategy, and we need a very good mathematical framework to map easily this problem to what we are doing we are talking. Okay. And also, what we can say that yes, this hybrid quantum computing from DWave are already capable to address a real-world optimization problem in aviation sector and another sector that is important. And also the result that we have seen and making the benchmark, and we are working in the paper that we will see the paper in the coming weeks or months, comparing to the best classical solver are very, very, very promising and is very, very interesting. And we have seen in some cases that this strategy and these results are better than some classical solver. Okay. And the platform that we are designing also, this shows that we can make it extensible and we can make it adaptable and scalable. That is very, very important. Also, one thing that, and in the scientist way, we have to say it, jump to what we have done here to the gate-based solvers is very straightforward. The thing that we need to do is only the little change of a variable that we know by Ising model. So taking this objective function and the penalty, all this stuff that we have, and design some kind of little variable change here that mapping the binary variable that is 0 and 1 to the Ising variable that is minus 1 and 1, we can send directly this problem to the another type of quantum technology that is gate-based technology. The only thing that here is that those computers now they have like few qubits and they cannot tackle this problem. Okay. Nonetheless, that we achieve a lot of things, let us say that we are keep exploring universal way to solve this and long-term strategic investment to keep making progress in this field. Now we are in the question and answer, and if there's a question, I will be very glad to take some.
Great, thank you, Parfait. We actually have quite a few questions. It was a very interesting talk. There were a few questions about kind of quantifying what the benefits would be of this approach. So basically, by improving 4 to 5, 6% in terms of the utilization here, how does that translate into revenue or efficiency gains or whatever for an airline like Vueling? Is there a way to quantify that yet?
No, to be honest, not yet, but I can say a few words that can help us. If we remember at the beginning, we had like a long-term strategy, a mid-term strategy, and we have the tactical strategy that is the very short terms. It's like a day before the departure time. But we say that the long-term strategy, all this stuff was like manually. So, and the optimal was no guarantee. There's a lot of things here. So, what we are saying here is with this framework and all this stuff, we are giving some kind of indicators that can show that, wow, we have this bunch of candidate of solution that they can go to this bench and they can see directly the sub let us say that the sub rotation or the group of the sub rotation and to see easily and compare it visually with the original network and they can see the grain. But here to be scientists oriented, we didn't do it, but the idea is the grain will be proportional to the percentage of retirement that we were talking about.
Okay. We had a question about any recent published articles or papers on quantum optimization of aircraft routes. I think, did you mention that you're going to be posting some information, and are you aware of any other papers out there at this point?
Yes, we are working. We already have a paper. We are in the process of uh, of reading and adjusting and so on. And we will share the result in the coming weeks and coming months. But the idea is that we will release the paper before Qubit Summit. This is sure.
Great. And actually, so I will give a little plug. So DWave's annual user conference called Qubits will be held January 27th and 28th in Boca Raton, Florida. The first day will also be streamed. The second day will not. We'd love to have you all come and attend. And if you go to qubits.com, you can find information about the conference. The agenda is being built as we speak. And everybody that has always attended has always found it very worthwhile. So take a look at qubits.com to find out more information about the annual event, which will take place in Boca Raton, Florida. Not a bad place to be in the middle of winter if you're in the northern climates. A few other questions, actually quite a few other questions. Someone is asking what the Vueling fleet size is.
Yes, and this information can be found in internet. We are talking about for 400 size,
Okay.
400, yeah, close to.
The question is about constraints for weather, staff scheduling, fuel refilling, and inspection time. Are any of those considered in this model, or is that part of the additional work you're going to be doing?
Totally. Here, and the maintenance and all this stuff are considering in the sub rotation design. So is what we are saying that if we remember, we can remember. If I can go back quick here and here here, what we are saying that we already, once we generate this, all these constraints, we have this constraint and we can add more constraint here. So, and this constraint here, we will not put all these, weather, all this maintenance and stuff. All the maintenance stuff will be generated here when we are designing the sub rotation and stuff.
Okay. In terms of the status of this work, is the system in use or is it more of a POC?
Everything that we work from Lighthouse, what we do is like we design some kind of POC and we move to some kind of MVP. So what we are doing here is yes, consolidating an MVP, and from that we need to to explore like some problems, additional problems to move this MVP to the production stuff. So this project that we have done is like is framed like the technological assessment framework, innovation assessment framework, and from that we are moving to MVP.
Great. Someone asked about the data set and whether it was available publicly.
I don't get so because here is something that we need to discuss with Vueling and if this fit in the Vueling strategy or not. Okay.
Okay, so it is not currently publicly available.
Currently, it's not public. It's not public.
Okay.
It's private. Yeah.
We had quite a few questions regarding comparison of this approach with using the DWave hybrid solvers versus strictly classical. So can you comment on that?
Yes, we have done, and the paper we have it deeply. I did it as this was like some kind of webinar. I didn't want to touch the competence or competitive brand, not, but um, for the few let us say that few variables, and the classical solver are dealing very well. Okay, but the problem here is that the classical solver has also some kind of constraints, like when you are dealing with more than, when you are close to 1 million variable. Okay, it's easy to have 1 million variables if you don't design very good strategy, and the way also that you model, you have the model. Okay, so comparing what we have seen, we had like the classical solver like a reference, and we compare to the quantum solver, and what we have seen is using the BQM, that the BQM solver, and there was some places that the classical solver beat a little easily. Okay, but when we was using the CQM, the quantum solver was achieving the same time, at the same time, the same optimal solution. And we try to model some another problem that was not fitting here, to see how the classical computation solver behave against to the quantum solver, and we saw that the CQM behave better than the classical solver.
Okay, time for just a couple of more. In your results section, you mentioned how your algorithm added new flights compared to the original flight schedule. Wouldn't this be a bad thing? Isn't the point of the scheduling problem to keep all of the routes and demand satisfied while minimizing the number of aircraft?
And I didn't get well the question. The question is if the output or the outcome that we have like a new flight, if this is bad for the
Or
model.
more, or if there are more flights as a result.
Uh, it's not bad. It's not bad. That if we can see here in this slide that I'm showing, this is some part of a strategy. So you have the original network, and here we define some kind of set of optimal flight that are not, but they are optimal, and we put in the model to push the original flight that is hand based, to push them and to see how can we modify this original flight and to find the optimal one. By doing this, we can achieve some new flight that yes, new flight that's sub rotation, that the operational team can decide if they can keep this or not. So it's not bad. It's giving like a new opportunity to 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 have like a, let us say that, a highlight of the business model, and also to decide what they can do. And in the case of having like a more optimal candidate to define the last decision optimal schedule, also is good for the optimal team. So it's not only straightforward that this go through the model, they apply it directly, because you can lose a lot of money by doing this. But there's some kind of committee, of flight committee, that have this outcome, and they analyze this outcome, and they can make a decision that yes, perfect, let us do the one, or does it do the another, or let us do the combination of the output that we have.
Okay. We only really have time for a couple of more. To everyone else who asked a question, I will send these along to our team and try to get questions answered over email. There were a few questions here, very interesting ones about energy consumption. You know, one of the great advantages of quantum computers is the energy consumption is very low. It's basically what it costs to or what it uses per day for the cooling system and the front-end servers, which is, minimal versus using a high number of classical solvers. Is this something that you have any information on, Parfait, or you have considered?
This is a very, very good remark, very good remark. But in this work, we didn't consider this, but we know it. We know it that one of the good things that people doesn't remember easily about quantum computing is that the quantum computing is very sustainable, or what we are trying to do is that to make quantum computers very sustainable than a classical computation, because they are very efficient in that way. Okay. But in this work, we didn't measure that. But it's very good. It's very good to do that, to say that, because sometimes a lot of people, when they think about quantum computers, they think like, yes, maybe it will be go faster, it will quicker, it will that. But maybe this is not that important. If you can achieve the same result with less energy, also you are doing a very good stuff also. This is very good, a very good question. But
Yeah.
here we didn't measure it because we didn't have like the input information of some kind of instance where we were sending the the problem. But we do measure the variable, the numbers of variable, the size of the problem. All this, yes, we have done it. But for the energy consumption, we didn't do it. But very good, and very, very good question.
And the last question here, do you believe that this approach is way more scalable than classical approaches?
Um, I think that I think yes, but let us be like scientists, so politically correct, okay? Classical solvers give us exact solution on somewhere. Okay, we are saying that the C plus Groby is exact solution. So they are based like a simplest way to solve, like a linear programming, and they use some kind of technique to move from the linear programming to the integral programming by making some kind of code and using three structure. This is what how Groby and C plus or Doppler are working. Quantum solver, or the solver like the DWave solver, is some kind of, let us say that is a heuristic solver. Is a heuristic solver. That is another way to solve the problem that we have. Instead of seeing all in details that this is better or not better, we can say it easily. We can say that we have another approach to see how can we solve the same problem, where the tree structure for amount of variable could be stuck. Okay, this classically could be stuck. And this heuristic way to solve that we have, like by the solver from DWave, can be very interesting. And also, if we use some kind of quadratic modeling, we can explore very deep problem and a huge number of variables without stocking like a classical solver base in tree and so on. So the thing that I would like to highlight here is, for the closed feature, sure that the heuristic solver could be it, because if we don't have the ability to see how can we speed out this tree-based solver, that the tree grow up very quickly and stock exponentially about the number of variable. I guess that this stochastic solver, taking account the quantum tunneling and also using like some kind of simplest model to find like a hybrid computation, could be the the most interesting solver for the next years.
Okay, well, thank you so much. Again, a few things. We've recorded this session. If you go to DWave's YouTube channel by late today or early tomorrow, it will be there, but we'll also send out an email to everyone who registered with a link to the recording. You can keep your eye out for a paper. That sounds like it'll be a couple of months before the paper is out there. But we thank you all for coming, and we will be sending information about next month's webinar as soon as we can. So thank you all, and Parfait, thank you so much. And we look forward to hearing more about this project as it moves into production at Vueling.
Thank you.